Hi, I'm TJ Mullen, and I'm the president of Best Management Products. I'm going to talk to you today about structural stormwater quality improvement for turbulence reduction and increased sediment, trash, and hydrocarbon capture. The goals of this presentation are to understand how structural methods can be used to improve stormwater quality, to learn about structural stormwater device options, to discover how to apply various control options to target pollutants of concern, to learn how to correctly specify and size products based on flow parameters, to grasp how using multiple control technologies can best reduce pollutants, learn how structure design impacts removal efficiencies, examine hydraulic impacts of water quality control devices, understand retrofit and split device options for constrained access structures, learn key points about the installation and maintenance of water quality devices, understand resources available on bmpinc.com, and to cover case studies and learn from previous applications. BMP has been around for over 20 years, and we got our start in 1999. Our very first commercial installation was actually at Haverford College in Pennsylvania, and we were lucky enough to have it be featured in the Field segment in Civil Engineering magazine. We've always featured cost-effective stormwater quality devices for the urban and ultra-urban environment. We really emphasize capturing sediment, trash, floatables, and hydrocarbons. We have more than 80,000 installations throughout North America. Why use structural methods for stormwater quality improvement? Well, urban and ultra-urban environments may not have the space available for land-based systems, such as infiltration fields or ponds. And structural methods can also be used to target specific pollutants. They're also well suited to serve as pretreatment for larger storage-based systems, and they can reduce the ongoing maintenance or boost the performance of those systems. And structural methods also offer the most flexibility as far as BMP placement on your site. What is a structural BMP? A good working definition is a facility or structure that is stationary and permanent, that is designed, built, and operated to prevent or reduce the discharge of pollutants in stormwater runoff. In this picture shown, there is a snout hood covered by a stainless steel trash screen. This facility is at a Navy base in Annapolis, Maryland. The primary BMP components for water quality improvement that we're going to discuss today are water quality hoods, such as the snout, turbulence reducing sump plates, such as the turbo plate, hydrocarbon reducing booms, such as the bioskirt, and full trash capture devices, such as the stainless trash screen. How does a water quality hood work? Water gets into the structure one of two ways, either sheet flow through a grate or from upstream through a pipe. What happens is the runoff enters the structure, and the floatables and the oils will rise to the top, and the heavier particles will sink to the bottom. The hood prevents the surface pollutants from exiting the structure because the water leaves the structure where the bottom of the hood is. The snout hood has a feature of an anti-siphon vent that prevents the water from being drawn down to the bottom of the hood. And if that was the case in a high flow event, all of your captured surface pollutants could also be drawn downstream. Because of the anti-siphon vent, the static water level in the hood is always going to be where the bottom of the outlet pipe is. So you're always going to maintain a separation layer that's defined by the bottom of the outlet pipe and the bottom of the hood. So that traps your floatables and your trash on the surface. Your sediment and gross particles, your heavy solids will sink to the bottom, and the water will always leave from that separation layer in between. Examples of how hoods can be used in structures. The picture on the left, you see a hood trapping floatable debris primarily. This is near a loading dock at an office supply store. Trapping floatables and trash are one of the most common applications where hoods are used. Hoods can also be used in smaller ID structures like this PVC structure. The NP series of snouts can be used in these smaller ID structures to trap floatable debris, oil, and other surface pollutants. In the picture on the right, you can see a snout with a bioskirt. It's employed in this application to trap oils and natural pollutants that are floating on the surface, like pine needles. The snout hood specification. Key points are the snout size is always going to be bigger than the nominal pipe size. The specification also lists the material requirements of the snout, the sump depth. It lists that the pipe should be finished flush to the structural wall, and it mentions the position of the snout. It also provides installation details and other important information. Structure considerations for sumps with water quality hoods. It's important to think about your structure and the sump depth. And again, by sump depth, we mean the distance between the bottom of the pipe and the bottom of the structure. Our general recommendation is to have a minimum sump depth of 36 inches for pipes that are 12-inch ID or less. And then once we get beyond 12 inches, we recommend a sump depth of at least 2.5 times the pipe ID. So for instance, if you had 24-inch pipe, we would recommend a sump depth of 5 feet, which is 2.5 times 2 feet. And that would be from the invert of the pipe down to the bottom of the structure. There's a lot of things to consider when sizing a sump. One of the things is that the scour depth from the static water level is going to be 12 and typically 18 inches beneath the static water level under a high flow event. So you want to make sure that the sump can accommodate that, because if you have a 36-inch deep sump, then you really only have about 18 inches of useful storage space. So a deeper sump means less frequent maintenance, and that's important. Also note that the hood is not just sized to cover the outlet pipe, but it also has to handle the flow. And we have a hydraulic sizing table that will help you with that. The other thing that's important to consider is the position of the bottom of the snout hood relative to the invert of the pipe. We recommend at least half the pipe diameter beneath the invert of the pipe for the bottom of the snout hood. That means that if you have a 12-inch pipe, we need to see the bottom of the snout at least 6 inches beneath the invert of the pipe. More is always better because you create that separation layer where your floatables and oils will accumulate. So the deeper the separation layer, the more effective the snout installation will be. So snouts can fit flat structures and they can fit round structures. For flat structures, basically you need to cover the pipe, you need to account for the flow, and then you need to make sure that the snout is not wider than the wall of the structure. For round structures, it's a little more complicated in that you need to make sure that the back of the snout will match up with the curvature of the structure. So this drawing, which is available for download on the website called Snout Relative Sizes All, takes you through the various R series snouts, and the R series snouts are for round structures, and it specifies what size structures they will fit. So it's important to know when you have a round structure that you're not only covering the pipe, and again, the snout size is always going to be bigger than the nominal pipe size, but you also need to make sure that the curvature of the given snout matches the curvature of the structure that it's going to be installed in. BMP has a number of split parts that are designed to fit through structures with constrained access. That can be important, for instance, if you have a situation where you might need a 24F snout to fit through a 24-inch manhole opening. Well, that's not going to work because the snout's 30 inches wide at its base. But fortunately, we have a number of split snouts that are split in 2 or more pieces that allow you to basically fold them into smaller size openings. And also that's true with turbo plate sections as well. We can get these through 24-inch openings. Not every snout, the biggest size snouts, that's not possible with, but for every snout up to 30 inches, which will cover a 24-inch pipe, we do have a split snout option that will allow you to get them into a structure with constrained openings. So take a look at the split snouts on the website, and all of the part details are downloadable there as well. BMP makes a variety of specialty snouts. Now, these hoods are for special applications. For instance, a pipe that exits the corner of a structure. We have the 24C corner snout. That's really a project saver in many occasions. So if you run into a corner structure or a structure that is square or rectangular and a pipe exits a corner, the 24C snout will accommodate up to an 18-inch pipe leaving the corner of a structure. We also have low profile and sand filter snouts. These snouts really limit the protrusion into the structure, but while they are low profile, they also don't have a lot of conveyance capacity. So these would typically be used for a maximum of an 8-inch ID pipe. We also make snouts for small diameter structures. Typically, you might think of these as PVC drainage structures. They're available for 18-inch ID, 24-inch ID, 30-inch ID, and 36-inch ID structures for a variety of pipe sizes. So those small diameter snouts are also available with details that you can download on the website. When you add a water quality function to any stormwater inlet, you'll have a hydraulic effect on your system. BMP provides a live spreadsheet where the user can plug in flow values in CFS and feet per second and get a head loss measured in feet and a K factor for your hydraulic model. So this is in the hydraulics folder on the website at bmpinc.com. And if you have any questions, we're happy to help you use the spreadsheet, or you can give us the flows and the velocities. We'll input them and generate a report for you. Note that if you have a snout and the flow is beyond what we recommend, then just upsize the snout to accommodate a higher flow. Our largest snouts can accommodate in the neighborhood of 100 CFS. So we have a snout that generally is going to fit your application. Now, once you get beyond 100 CFS, we may recommend that you break that drainage into a number of runs and then use the larger snouts over multiple outlet points. So that's the recommended option there. But we will provide information for you, or you can calculate it using our spreadsheet for what your head loss is going to be and what your K factor is going to be for a snout in a structure for your drainage run. So we highly recommend using snouts and bioskirts as a standard practice prior to discharge in any underground storage system or a pond to reduce maintenance. It's an easy retrofit. You basically want to keep the service life of these facilities as long as possible, and reducing the loads of sediment and trash and gross pollutants in structures upstream. Make sure that the downstream structures, whether they're underground or ponds, can be as efficient as possible. And nobody wants a pond to be a trash swale or a trash collection pond. Obviously, the aesthetic benefits of a pond then are completely lost, and that would be true with a bioswale as well. And in fact, that the overburdening of an infiltration practice can reduce the service life of that infiltration practice. So getting stuff out upstream, especially for underground systems, is really important. So structures with snouts or hoods and bioskirts prior to discharge into these storage facilities should be a mandatory practice. Is it possible to retrofit a structure with no sump? Yes, it's possible. Two options are to build an internal wall and put an orifice on that wall and then put a sump. Then the sump will be defined by the elevation of that orifice, and you put a snout over the that internal wall and over that orifice. And then the other option is to put a small snout upside down, inverted, if you will, and then put a larger snout over that, and that will create a sump in the structure. Now, in either case, your sump depth is going to be, limited by either the orifice invert or the top of the inverted snout. And you're not going to have a lot of volume. There's not going to be a lot of volume to capture your collected materials. So keep that in mind. And you will want to maintain a structure that has a retrofitted sump much more often than a normal structure would be. So to get back to water quality structure design, we think of a drainage network with sumps and snouts as an enhanced drainage network, whereby you're setting up a structural treatment train. So we recommend adding sump structures wherever possible, or at strategic nodes where different pipelines might come together. And removing pollutants incrementally at various entry points, for instance, inlets, benefits the downstream facilities that rely on higher resolution removals, so you're not overburdening them with gross pollution and trash. The structures upstream typically will have lower flow, and you remove the pollution incrementally along the way, so not everything is left to the final structure where you're overwhelming a structure and really then asking that structure to handle smaller particles that are more difficult to remove. If you remove them incrementally along the drainage network, it's much easier with simple methods to have a greater impact on overall water quality. So it's important. And, for these applications, there are various states that award certain amounts of credit for snouts with sumps. And one example is in Pennsylvania, where you get a reduction of 60% for TSS, 50% for phosphorus, and 20% for nitrates. So when you're providing a structural treatment train, and by that, I mean removing pollutants incrementally with a variety of structures along the drainage network, that's an enhanced drainage network. You can think of every sump structure as a micro detention node. So you're putting sump structures in your drainage run wherever possible, or at strategic nodes, meaning maybe some pipes are coming together. So you want to remove pollutants at entry points as much as possible, meaning inlets. And this will benefit the downstream facilities by preventing them from being overwhelmed from gross pollutants, especially if they're targeting dissolved constituents or real fine particles. You don't want these higher end facilities being overwhelmed with gross particles. So the structures upstream will reduce the burden of downstream structures. And that's the point behind an enhanced drainage network or a structural treatment train.